Okay, so we're going to talk about inverses of functions, and I think we've had a bunch of examples about functions. When you think about the inverse of a function, you're thinking of the kind of the reverse process. So we'll get there. But first of all, we use the vertical line test, or we can use the vertical line test. So here's the graph of a function, and we can use the vertical line test to determine if it is a function or not. And so once you know something's a function, you can then be more specific and call it either a one-to-one or a many-to-one. So the way we can describe this is that a one-to-one function is there's only one input for every output. And this is kind of the reverse of the description of whether something is a function or not. Because if it is a function, we say there's only one output for each input. So you see how those are just kind of reversed. Many-to-one is when there's going to be several inputs for one output. So this would fail the horizontal line test. This would pass the horizontal line test. So for example, our function up here, the parabola, would not pass the horizontal line test. We would call it a many-to-one function because several inputs for one output, meaning, let's say for this value of x, y is this, but there's the same value of y for a different value of x. So many to one, meaning many more than one value of x, gives us the same value for y. Okay, so here's a sort of an imaging diagram, or whatever we call these, where we have different inputs, like 2 and 3, leading to the same output. So this would be many to one, so there are several, or at least more than one. I know that 2 doesn't sound like a lot, many, but it is more than one. So we have several inputs leading to the same output, whereas if it's one-to-one, each output has a distinct input. So not like here, 2 is comes from both 2 and 3. Examples of graphs. So this passes the horizontal line test. This does not pass the horizontal line test. Okay, and I think we have examples. So here's an example. So practical. Like, what are we talking about? So if we talk about you growing, so this is while you're still growing, not while you're an old person like me, right? And I'm stopped growing, or maybe even I'm shrinking. I'm not old. So, but this is you, and you're still growing. And so we could talk about height as a function of time. And so, well, the x-axis would be somewhere down here because you don't have a negative height, but your height, so you're growing quickly, and then you're still growing, but not growing as fast, and then you're still growing. So for any given height, there's only going to be one. So for a given y value, there's only going to be one specific value of time that you were that height. Now, if you talk about being an old person and then shrinking, that all of a sudden changes. But for you, as a growing adolescent, it would be a one-to-one function. A many-to-one function, so this might be something like temperature as a function. So temperature as a function, so I'm saying first, day of the year. So here we are in, I was going to say September, so here we are in October, and the temperature outside is, let's say, 60 degrees Fahrenheit. And then, it gets really cold in winter, but then it starts warming up, and by the time we get to, all of a sudden, here's some day in February, temperature is 60 degrees as well. So that would be a many-to-one, because for a given temperature and output that we're talking about, like 60 degrees, there are going to be several days at which the high temperature is 60 degrees or something like that. Probably. Okay, so just some graphs so you could try these. Examples are these functions, and if it is a function, is it many-to-one or one-to-one? So for this, we would say, yes, it's a function. It passes the vertical line test. And is it many-to-one or one-to-one? It's going to be many-to-one. You see how I'm abbreviating that? M-to-one, many-to-one, because it does not pass the horizontal line test. So this fails the vertical line test, so not a function. This does not pass the vertical line test, so we would say it is not a function. For a straight line, this definitely passes the vertical line test, and it passes the horizontal line test. So it's definitely a function, and we could call a 1-to-1 function. I like that abbreviation. Okay, here we have a square root function, and that definitely passes the vertical line test, and it passes the horizontal line test. So the square root function doesn't continue down, but it keeps going up. So that's cool. It's a function, and it's a 1-to-1 function. Next up, our parabola is a function, but it's a many-to-one. And our other square root function is also a function, and it would be a 1-to-1. For the cubic function, that's definitely a function, and it's also 1-to-1. When we get into more advanced cubic functions, they actually look like this thing over here. Where, hey, come on, what's going on? Oh, that's the eraser button, sorry. That one could be a cubic function, so it would still be a function, but in that case it would be many-to-one, but because this doesn't dip back down, it's a 1-to-1. And here we have some piecewise, so let's see. If this, I think I was trying to draw a horizontal line here, so if that doesn't look quite horizontal, just tip your paper until it does, thank you. So this would be a function because it passes the vertical line test, but because here we have, for the same output value, we have several different inputs, so this would be a many-to-one. And here does pass the vertical line test and passes the horizontal line test, so it would be a function, and it would be 1-to-1. Alright, so next page, let's talk about and what the inverse means. I'm sorry, let's talk about that soon. So let's see, these, hopefully I can retrieve these soon. So are these functions, sketch a rough graph, if it is a function, is it 1-to-1 or many-to-one? Alright, so this is kind of arbitrary, but I like these because we're talking about input is first name and output is height. So being at Mammoth High School, you know, for several years we've had situations where each first name is individual and distinct, but that's kind of a rarity. So I graphed it something like this, where I would have names down here. This is Joey, and this is Josephina, and this is Zach, and this is somebody else. And so the height, well, oh, there's two Joeys. So this Joey has this height, but that other Joey has this height. Josephina, there isn't another Josephina, so this is her height. But who's this other person? Zach. So there's this Zach with this height, this Zach with this height, this Zach with this height. So this is not a function, because for each input value, there is not a distinct output value. So I said, no, it's not a function. And if it's not a function, talking about 1-to-1 or many-to-one doesn't make sense, because that only applies to functions. Fingerprint, however, these are distinct in age. So here's my fingerprint, and here's your fingerprint, and here's her fingerprint, and here's his fingerprint, and so-and-so's fingerprint. And each of our fingerprints, it corresponds to one specific person, and that one specific person has one specific age. So this is both a function and many-to-one or 1-to-1. Well, you could have somebody else that has your exact same age. And so I guess, you know, identical twins, let's just not bring that up. But somebody else across the world, Mr. Chang was born on exactly the same time that I was. So even though we have different fingerprints, we have the same age. So that would be many-to-one. Number of hours you have worked and total pay you have earned. So if you're working for an hourly wage, the graph of it would look something like this. 0, 0 is a point. You don't have a job, you don't earn any money. And this could be argued, you know, if it's salaried. Well, okay, I'm gonna stay on task. All right, so this is a function, yes, and it would be 1-to-1, because for every specific paycheck you get, that corresponds to a specific number of hours that you worked. Number of days you have lived and your height. So here we're talking about you're still growing, and it might look something like this. Actually, in the adolescent you may have some growth spurt or whatever, but we're assuming that you keep growing, and so this is a function, and it would be a one-to-one, because for any specific height, and we're not talking about like 5, 6, we're talking real microscopic, lots of decimal places. For any specific height, you would have a specific age. As you get older, your height increases. And then classroom and height. So I think I was talking about like this is Tourville's classroom or O'Neill's classroom or whatever, and then the height of the actual classroom. And so I think that the rooms are taller in the spa. So this is the spa building. So here's my classroom, and this is O'Neill's and Miss Garcia's. But then in the normal high school, this would be Leigh Fran's room and Cooper's room, and there'd be a specific height. So this is a function, because you're never going to have one classroom that has two different heights. Although if you look up at the ceiling, that could be argued because my ceiling is slanted. But we have to simplify things so that we can actually talk about them. So we're going to say, yeah, that's a function, and this would be many to one, because there are definitely several classrooms that are going to end up with a height of 8.5 feet or whatever it is. Okay, so just some practical examples talking about those things. So lastly, inverses. The idea behind an inverse is that it's a reverse process. And so in English, you're basically going to switch x and y. And then in math speak, well, yeah, you can read that. I don't have to read it to you. But the example, Joey earns $8 per hour, and so we were talking about that. He's working for below minimum wage. So the function would be money earned as a function of number of hours worked, right? If he works for 10 hours, he earns $80. And then the inverse of that would be the opposite, meaning we're talking about the number of hours worked as a function of the money he earned, which we could figure out. If you know that he earned $800, you know that you could figure out that he had worked for 100 hours. Mathematically, in terms of equations, we basically switch x and y. That's the bottom line. So here's our function. I'm going to write this in terms of y. I'm going to switch the x's and y's, and then I'm going to get the y all by itself, and that's our inverse. So I subtract 8. I take the square root of both sides. So this is my inverse, and to be mathematically correct, I'm going to call it f inverse of x. So that little to the negative 1 means inverse. And so, some people are very verbal learners, and you can say this to yourself. So the function is square and add 8. So square and add 8. And think about what the opposite of that is. The opposite of squaring it and add 8 is square rooting and subtracting 8. Aha! Cool how that works. All right? Let's move. And then let me talk about this right here. So that's one thing to discuss. And then the other thing to think about is that inverses, so I said switch x and y. So one thing, another way you can think about it is if you take any point, for example, if this point were 10, that looks like 10, 1.5. All right, 10, 1.5. And if you switch the x and y values, you get 1.5, 10, which is over here. 1.5, 10. And so let's just ignore, let me see, I'm going to get some white ink if I can. Yep, there you go. Okay, so some white ink, and I'm going to cross out, because this is like a domain, not taking the square root of a negative thing. So I'm going to cross out. Let's just pretend that doesn't exist. All right, cool. So when we're looking at these graphs, inverses, we're switching the x and y coordinates. And then the other way to think about this, and you could do the same for other points, such as 25, 4, we'd switch x and y, and we get 4, 25, and that point's going to be right here. Cool. So the last way that I'll talk about thinking about these is that we talk about reflections. This is the line y equals x, And so inverses are going to be reflections across the line y equals x. So you can see I plugged these equations into Desmos, and you can see how if you were to take the blue graph and flip it over that line, we'd end up with the red graph. Cool. Okay, so a couple ways to think about this. Switching x and y coordinates, reflecting across the line y equals x, switching x and y values, and solving for y in terms of the equation. So last example here, we have y equals 2x minus 10. I switch the x and y values, add 10, divide by 2. So here's our inverse, and see how I'm not calling this y, I'm calling this f inverse of x. And so in terms of the words, let's see, our function is multiply by 2 and subtract 10. I'm going to actually write that. So multiply by 2 and add 10. So if we were to do the opposite of that, we would say, well, I'm probably going to divide. Instead of multiplying by 2, I'm going to divide by 2. Did I say add? You know what I meant. Subtract. I was jumping ahead of myself. I divide by 2, and the opposite of subtract is add. And add 10. So we're adding 10, and we're dividing that all by 2. All right. So opposite processes, and if we look at, this is going to get messy. If we look at this graph, so I've graphed both of these again on the des. So 2x minus 10 and x plus 10 over 2. And so you could do that flip-flop with coordinates of a specific point, like 20, 15 and 15, 20. Cool. And if we were to graph the line y equals x, so just 45-degree angle, passes through the origin, has a slope of 1. You see that those are definitely flip-flops. And then the other thing that we notice about when we were reflecting across different axes and across different lines is if they cross the line over which they are reflecting, they intersect at that point. Okay, so I think that's all I have to say. I'll just give you some advice. There are a couple homework questions where y shows up in 2 locations. So like if this were the function and we were finding the inverse, we would switch the x's and y's. And in general, students kind of have a difficult time isolating y in this situation. So now that we're here and I have your attention, I'm just going to solve this one out because this is similar to some homework questions. So in this case, I would multiply both sides by this to get it out of the denominator. So first, get rid of that fraction, right? Fractions are difficult. This gets distributed. So we have xy plus 3x equals y plus 2, because those canceled. And then you're like, well, how do I get y all by itself? It's in 2 places in the equation. And so kind of a trick is we can move everything else to one side and move any term involving y to the same side. So we end up with xy minus y. So I subtracted the y to bring it over here, and I'm going to subtract 3x to bring it over here. And this is helpful to us because, I know it still looks messy, but the trick here is we can factor out the y, because if we factor out the y, we can all of a sudden divide by that thing. So we factored out y, and we have y times one thing that we can then divide by, and voila. Y ends up being all by itself. That's cool. 2 minus 3x and x minus 1. And so technically we would call that f inverse of x. And if you're saying the words to yourself about like what are we doing, it gets a little tricky when there are 2 variables, or when x is in 2 locations. But anyway, you can do it. Thanks.